This is Electrical and Computer Engineering Team 2213 working jointly with Mechanical Engineering Team 15 on the Compact and Robust Data Logger project sponsored by Collins Aerospace. The team is composed of 3 ECE members and 1 ME member. From left to right is Michael Benvenuto, Computer Engineering, myself, Jeremy Amoro, Electrical Engineering, Rigel Watchman, Mechanical Engineering, and Diego Vilca, Electrical Engineering. The reasoning for this project is that Collins Aerospace needs to test their devices and equipment in environmental chambers to simulate the conditions on aircraft to ensure correct operation. Our team must design and construct a data logger to monitor signals of a device under test while withstanding temperature extremes in an environmental chamber. The requirements as given from Collins Aerospace are: the data logger shall withstand long periods of time at temperatures of -40 degrees Celsius to 85 degrees Celsius, collect data from 4 analog inputs. These analog signals can come from sensors that provide measurements of the environment. Data can be of plus or minus 15 volts with a frequency of 1 megahertz, be compact and displayless, store data on and load settings from a removable storage device, and be able to self-calibrate. Other off-the-shelf loggers are not suitable for this operation as they are constructed out of non-temperature resistant materials, low sample rates, are stationary, and do not feature onboard memory storage. Here is our design. The top image is a 3D rendering of our data logger printed circuit board, and below it is a picture of the final product. There are 3 main sections to this board. First is the analog section. On the left are 4 twin BNC connectors for each of the 4 differential analog inputs. Each input then has an amplifier with programmable gain to attenuate or amplify the input signal. The signal then goes to an analog to digital converter that will allow the signal to be processed by a computer. Next is the digital section. The main controller of the data logger is a Xilinx FPGA with a dual-core ARM processor. This chip facilitates capturing the data from the analog to digital converters, controlling the gain of the amplifiers, the status LEDs, data transfer to and from the SD card, signal processing, and data compression. The third section is the power section. The board is powered via 5 volts from a USB-C input. There are 6 onboard voltage regulators and a power sequencer to create the different voltages for various parts of the board. Here is a high-level example of the SD card output data from the data logger. The first line is where the user will input settings such as sample duration, triggering, sample rate, and gain settings. The data logger then marks the start time and starts to save the data in lines 3 and onward. When logging is complete, the user can take the SD card out of the device and plug it into the computer for viewing and doing additional signal processing and analysis. Lastly is the mechanical engineering side of the data logger. The mechanical engineering team designed and constructed an enclosure to protect the electronics from the temperature extremes during testing. The enclosure features a conductive coated glass viewing pane for viewing the status LEDs and a conductive gasket seal around the lid so the enclosure acts as a Faraday cage around the data logger. The enclosure is able to be hung on mounting points with small hooks on one side. 2 secure latches ensure a tight seal and easy access to the micro SD card inside. There are 2 versions of this enclosure being made. The first is an aluminum CNC'd enclosure, and the second is 3D printed out of a nickel alloy.